Okay. Hi, everyone. Welcome to this workshop in machine learning in Python. So here's how I've divided this workshop. In the first 30 minutes, we will try to build like an intuitive idea of what neural networks are, and then introduce some key concepts which can help solve our problems. You'll spend the next hour going through the Python code we sent out to everyone this morning, and then build a neural network. So a couple of pointers before we get into it. Uh, I would ask that you please hold off on your questions until we get to the end of the workshop, because over 40 people are waiting for the recording of this workshop, and there's a lot of material to get through. So I don't know if you'll be able to complete it in time with questions. I can hang around after the workshop to answer questions as long as anyone requires me to. I see a question in the chat. Okay, no. All right. And the second thing is this workshop only assumes basic familiarity with Python and a little bit of calculus. I'll try to keep it general. But people who know machine learning might find the first 30 minutes to be a bit basic and missing a few details. But I feel like there is value in knowing the intuition behind why these networks work. So moving on. So I'm going to use an analogy to talk about neural networks first. So let's imagine that you have the world's most complicated stereo. That is, you just bought this thing from someone and you don't know whether it's a scam or not, but you have it for now. And you are trying to play your favorite album on it. Let's assume that you have perfect pitch and that you know this album from back to front and you know every part of it. But what happens is that the songs start coming out very badly. Like there is this is not really a good audio player, and you're pretty disappointed that this pretty complicated stereo is not doing well. But there is a fix. The person who sold this to you says that there are 2,395,434 knobs on it. And if you tweak all of them, he says, they might eventually get better. So how would you even start this? How would you even begin trying to make the music sound better? Well, we could talk about assumptions first. Okay, I guess the first assumption is that you have a lot of free time. But apart from that, let's talk about the actual concrete assumptions. So you do not know how the knobs are wired inside the player. It's a black box of sorts. You know that if you like wiggle the knobs, sometimes the output might change, but you don't exactly know how they're wired or how they are connected. Also, the player doesn't really make random noises. It only plays from songs within the album. So you know that if it's playing something that doesn't sound good, it's because after this bit in this song, it's trying to play another song instead. You also know another thing. You know that which knobs affect other knobs values, and you know which knobs directly influence the output. So just to recap, you have this really complex player, which is playing very shitty music right now, and you want to try and make it better, but there is a fix. And the fix is to try and wiggle each of these knobs so that it gets a tiny bit better. Some of these knobs directly influence the music, but some of these knobs influence the other values. So how would you go about trying to do this? Your strategy would be to start off by wiggling all of the knobs and find out which of them directly influence the music, right? Okay, let's say there's a subset of knobs which do that. Let's say about 400 knobs directly influence the music. So you would first wiggle it one way, and maybe it gets worse when you wiggle it that way. And then you wiggle it the other way, and maybe it gets slightly better. So you just move it slightly to the other side, and then you move on to the next knob. And you repeat this for all 400 knobs. And by the end of tweaking all of these knobs for a little, you see that the sound is a little better. The song is sounding a little bit more recognizable. So your next step would be to try and find out which knobs control these 400 knobs. You know what I mean? Like you're trying to control the knobs so that in turn, the successive layer gets affected. Obviously, this is extreme overkill for a simple audio player mission like this, but you get the point. The expert recognition that you have of understanding what the song is supposed to sound like is helping you make changes to the knobs. And this in turn is helping you get better at this task. I feel like this is a valuable analogy because this is what leads us directly to the definition of machine learning and what could be a machine learning task versus what could not be a machine learning task. So the formal definition of machine learning would be that it is the study of computer algorithms that can improve automatically through experience and data. Now, the reason this is important is you need this particular trait in machine learning algorithms for it to work. You need it to be able to improve through experience. Let's tell you an example of what is not a machine learning task. If I gave you the picture of a coin and then I flipped it and told you the result, whether it was heads or tails, and I gave you a million such examples and I told you, I gave you the picture, then I told you whether it landed heads or tails, would you be able to tell me which side it would land on if I showed you a picture of a new coin? You would not, because it's not a performance that improves with experience. It's only clearly defined performance measures that improve with experience that can be handed over to machine learning algorithms and do better. So an even more formal definition, but one which is pretty easy to understand, is that a computer program is set to learn from experience with experience E. More people are entering. A computer program is set to learn from experience E with respect to some class of tasks T if its measure of performance, which is denoted by P, improves with E. So you need all of these things. First, you define a clear class of tasks. Then you define an associated performance measure. And then you find out whether experience in these class of tasks improves the performance measure. Only if all of these are true, then you can hand this over to a machine learning algorithm and it can try and get better at it. Thankfully, this is an extremely general definition, and therefore machine learning can be applied to a wide variety of problems. The main classifications of machine learning is to supervised learning, unsupervised learning, and then reinforcement learning. I would say the differences between the three are too much to get into for this workshop, but as a one-line definition, supervised learning is the type of learning in which you know both the input and the output. So our music problem was a supervised learning. You knew what the vinyl input is, and you know what it's supposed to sound like. And you essentially tweak the parameters of your network until what it's supposed to sound like matches what it actually sounds like. Unsupervised learning is when you don't know what it sounds like. Unsupervised learning is when you're trying to find patterns in the data. Maybe you're trying to find certain features in the data. And this is related to the research I currently do, which we can talk about after the workshop. And finally, reinforcement learning is a kind of learning in which there is an agent who is motivated by a reward. This agent has a certain list of actions available to it, and when it performs a few of them, it gets a reward. So it is reinforcing certain behaviors in the agent, and certain behaviors are being punished. And reinforcement learning agents have learned to play chess, Go, a lot of different board games, and that's a pretty fascinating subfield of machine learning. However, in our workshop for today, I think we will stick to supervised learning, and very specifically neural networks and supervised learning, because understanding the intuition behind these networks allows you to apply it to your own research or maybe to a wide range of general tasks. So what is a neural network? How do we learn this? Okay, let's start with what we call the hello world of neural networks, which is digit classification. All of these beautiful images are from 3 Brew 1 Brown, by the way. It is a YouTube channel, and this is from his blog. I would encourage you to check that out because his intuitive understanding of this really helped me to make this workshop. So first, instead of directly getting into what exactly it is and what different kinds of things it can be, let's first talk about objectives, like what we want the neural network to be capable of doing. So we know that the neural network is essentially a multi-input, multi-output function. So in the case of digit classification, this is the formal definition of the problem. You get a 32 by 32 pixel grid, which you can see in here. And each of these pixels corresponds to a brightness value. So maybe it's 0, maybe it's 1. You can see that when it's 0, it's denoted by just like a black dot. And when it is 1, it's denoted by a bright white dot. And any value in between is some shade of gray. So what you could do is represent all of these as a giant matrix, giant two-dimensional matrix. And we want the neural network to be able to take in this giant two-dimensional matrix, do something to it. We don't know what yet. And to be able to produce 10 outputs, excuse me, these 10 outputs correspond to the probability of the number being any of the digits between 0 and 9. And they are usually a number between 0 and 1 as well. So as you can see here, this neural network seems to be doing well because it's taking a handwritten 3 in and it's returning an output where all of the outputs are 0 except for the one corresponding to a 3, which is a solid white color. So how would you even begin doing such a thing? This kind of task is the task that is effortless for humans, but it's kind of hard to explain how to do to a computer. Especially when we formally describe it like this, it seems like wizardry. Like, how do you go from this big two-dimensional matrix to just 10 values? And how do I ensure that this works for all of those different numbers? Well, to do this automatically, first what you need is loads of data. There needs to be loads of labeled data, which is loads of these 32 by 32 pixel grids and their corresponding actual numbers. And someone needs to collect this data, like you need to have a data set. This in particular is a famous data set called MNIST, where someone has helpfully classified thousands of digits based on their pixel values and the actual digit being represented. Anyway, now that you have the data, I guess there's something you could try and do, but how? Like, how can you even start? What would be the first step to begin classifying these numbers? First, you could try and maybe divide the problem into sub-problems, specifically try and think about how humans identify digits. Like, how do you know that something is a 3? So I guess if you look on the lower right corner of this presentation, you can see that when we look at a 9, we're probably looking for a loop and then a line that attaches to it. Okay, so if I have those two, it's probably a 9. And then if I need to identify it as an 8, okay, there needs to be like a loop in the top half and maybe a loop in the bottom half. And if you have these two loops together, maybe that's an 8. And similarly for a 4, you want to break it down into like these combinations of lines. And this is what you want your network to do. Maybe you can train the hidden layer, so to speak, to recognize some of these loops and some of these lines, and maybe combine them all to give you a probability of what it is. That is our end goal. But do neural networks really learn this way? For that, let us talk a little bit more about the structure of neural networks. All right, so for our problem in this case, which is digit classification, let's assume that we pick 2 hidden layers. So these 2 hidden layers have 16 neurons each. Now, talking about neurons, what are neurons? So we don't need to know anything else except the fact that neurons are just a thing which holds a value. In this particular problem, they hold a value between 0 and 1. And this value is referred to the activation of the neuron. These are all terms which are derived from the biological counterpart of this neuron, which exists in our brain. Essentially, we were trying to mimic how our brain solves this problem and how it was so effortless for the brain. So maybe mimicking the structure of the brain could help us identify some digit like this. So what we did was we took 2 hidden layers. I mean, for this particular problem, for 2 hidden layers, and we connected the input. What we did was, the reason it says 784 there is we take our 32 by 32 pixel grid and we squish it into one long vector. That is, we just put all of the pixels in a vertical line. And then we connect all of those inputs to all of the neurons in the next layer, 16 of them. And we repeat this process from the second layer to the third layer. And finally, from the third layer to the output, we are going from 16 neurons to 10 outputs. That's a lot of connections. That's a lot of weights. And what we need to remember is that each of these connections, that is going from the first layer to the second layer, these connections have a corresponding weight associated with them as well. Okay, these are getting a little complex, so let's step back and try to analyze a single neuron in the second layer. Specifically, let's just pick a random neuron in the second layer and then see how many connections it has in it from the first layer. So we know that there are 784 values that should be connected to it, because those are each of the individual pixels. And each of these have a certain activation in them corresponding to the value of brightness in the original image. And each of these have a line connecting them to the successive neuron. This line has its own weight. So if you see a blue line here, that probably means that this weight is positive. And if you see a red line here, that means that this weight is negative. What that would correspond to is that when you increase the intensity of this neuron, the intensity of this neuron decreases because this is a negative weight. And if this is a positive weight, the intensities of these two are correlated. So how would you calculate the activation of the second neuron? Well, that would simply be a weighted sum of the activations of the previous layer multiplied by the corresponding weights. So you can see that W1A1 is this weight multiplied by this activation, and that forms just one entry in this matrix. So you would sum up all 784 activations and then come up with the value that is the activation of the second layer. Now, some of you here might notice a problem. You're like, I just told you that the neural network is between 0 and 1, but this value could put you anywhere on the real line. In fact, some of the weights are negative, so you could have a negative activation at the end of all this. What does that mean? Like, how does that cascade to the future layers? This is the reason why we use activation functions. So these are all bits of jargon related to neural networks that you will read in papers that use these particular methods. So these are known as the weights of the network over which we are optimizing. The reason I mentioned the analogy earlier is these weights are directly corresponding to the knobs in the audio player example. These are the things that we will tweak to eventually make the performance of the network better. If you wanted to visualize it in 2 dimensions, this could be the weight corresponding to each of the activation multiplied by the activation, which in this case is only this region here. So all of these weights would be multiplied by 0 and contribute nothing, whereas the weights in this region would be multiplied by a finite value and produce the activation for the next layer. Now, okay, we have all the entire real line as an activation for the second neuron, but we need it to fit between 0 and 1. So we multiply this whole output by this value sigma, which squishes the entire real line into a value between 0 and 1. So you would have heard of activation functions between layers, and this is the reason they're used, because X could be anything from minus infinity to plus infinity, and the Y value would put it between 0 and 1 based on its level of activation. So once you squish everything using the sigmoid function, you can guarantee that each of these neurons have a value between 0 and 1. And as they propagate, you can feel the effects of the previous neurons, but they will all be squished down to between 0 and 1 to keep the values of the neurons identical. So let's look at this particular example for now. There's some digit, we don't know what digit is being fed in. There's some miscellaneous levels of activations in these neurons, which are all just a result of like this big mathematical waterfall from behind. And then this feeds into the subsequent layer. And then finally, these subsequent layers lead to the output, where you get that this digit might either be a 4 or a 9. It really can't make up its mind whether it's between a 4 or a 9. So that's the first step of creating our neural network. We defined its structure. We said that they are all densely connected, which means that each neuron is connected to each neuron in the successive layer and the previous layer. And then we came up with this complicated structure and a lot of knobs for us to turn. Now, how do we get better at this task? How do we actually go from this to be able to classify digits? Well, going back to our definition of machine learning, there's one critical thing here that we're missing. We don't have a performance measure. We have a class of tasks. The class of tasks is to classify digits based on the handwritten image. The experience is the new digit that it sees every time. That is, it sees a digit and then it shows you an output, and you know what kind of experience it has learned from it. But you need to define a performance measure that is an indication of how wrong it is. Because right now, this is utter trash, right? Like what you would define the weights to be is completely random in the beginning. And we'll get to why we define the weights randomly. But anyway, if all of these weights are initialized randomly, and then you have these inputs going through here, the final answer will be complete nonsense. It would not be in any way a trained network. So you need to find a way to make it get better. And for that, we get into the topic of gradient descent. First, let's define a performance measure. Let's say that this was the input for the network, a 3. So what would you expect the output to be? You would expect the output to be uniform zeros everywhere in all other numbers except the number 3, which is completely solidly white. So this would correspond to a 1 here and zeros everywhere. And this is the actual output of the network, which is like numbers between 0 and 1 for all of 0 and 9. So how could you say what the cost of this difference was? So you could define a cost function that tells you how far away you are from the true value. And you could say that it is the actual value of the neural network's output minus the expected value squared. And the reason we have the expected value squared is we want this cost to be a positive function, and we want its value to be lowest when these values correspond exactly to these values. And we do not care whether the minus sign plays an impact or not. All right, that was a lot of things. So we now know that there's a cost function that can tell us how far away we are from the expected value. And we have this experience of dealing with different digits, like you'll get a cost for every different digit. And maybe you can use this to slightly get better. But how? How can you use the cost function to change your weight so that you get slightly better? Now, I'll bring your attention to an important thing. Let's say for a fixed input, that is this 28 by 28 grid of 3, and then for a fixed output, which is this, which is the actual measured output, uh, activations are fixed as they are just the summations of the previous layer or the inputs themselves. They don't have any freedom. So the activations cannot be whatever they want to be. However, the weights can be whatever we want them to be. We have decided that there would be weights in this network. So we can decide what the weights have to be. And that's the reason why the cost function can be expressed as a function of the weights finally. And this cost function can be minimized with respect to the weights to find the most optimal movement from the inputs to the outputs. That is, the cost function, when minimized with respect to the weights, will give you the best performance of this neural network on this particular set of handwritten digits. So we need to find the minima of the cost function with respect to the weights. So let's simplify our example. Instead of having how many ever 2 million weights or 13,000 weights or so on, let's just assume that our cost function depends on a single weight, just one weight. So that is the graph that you can see here on the right, where the cost function just depends on this one weight x, and you're trying to find the minimum of the cost function. So initially, let's say we start at x equals 0. How would you get to the minimum of this cost function? This is where I mentioned that we would need a little bit of calculus, because you need to find the gradient of the function at this point. Excuse me. You need to find the gradient of the function at this point, and that'll give you the slope of the function at this point. And what you could say is, if the slope of the function was negative, which it is in this case, then you take a step towards the right, because that'll make you go slower. I mean, go to a lower value. But if the slope of the function is positive, then you take a step towards the left, just a small step, so that you eventually find your way to the minima. And that is what is known as gradient descent. So you take the gradient of the cost function with respect to each weight, and you take a step in the opposite direction that the gradient is telling you to go. So if the gradient is negative, you take a step in the positive direction. And if the gradient is positive, you take a step in the negative direction. And eventually you will reach a point at which the gradient is 0, and that is the minima of the function. It is not the global minima of the function, but it's actually the local minima of the function. As if you started around here, and if you applied gradient descent step by step, you would keep going down as the slope would be positive. So it's telling you to go in the negative direction, and you would get all the way till here, but the gradient would be 0 at this point. You can never reach the global minima, which is over here, because as you start going back here, the slope becomes negative again, and it's telling you to come back to this point here again. This is one of the caveats of neural networks. There are no guarantees that the cost function you find with respect to the weights will be the minimum cost function globally. It will just be the local minimum. There are ways of dealing with this, but that is the reason I said that we try to initialize the weights of the neural network to random values, as you might have a higher chance of finding the global minimum by accident. I know that sounds like an approximation, but that is how it works. And unless your cost function is convex, you cannot guarantee that your minima that you found is in fact the global minima. Anyway, this is for when the cost function depends on a single weight. What if the cost function depends on multiple weights as it is in real life? So in this case, you can see a cost function which depends on two weights. So you can see that in fact, it's a cost landscape. And if you start at this particular point and you compute the gradient will tell you the direction of steepest increase. So it would point exactly in the opposite direction. So you would take a small step in the direction which is directly opposite to the gradient, and you would repeat. And you would repeat this process all the way until the gradient approaches very close to zero, and you know that you are in some kind of local minimum. This is essentially what a neural network does. You create a network which has a lot of these knobs that you can tune, and you have some mathematical guarantees for whether this input will produce the favorable output that you need, which we cannot get into in this workshop. But there are some guarantees that tell you that neural networks can approximate certain types of functions. And once you know that, you make small changes to these weights, calculating the gradient. We will not get into calculating gradient as well, because that is known as back propagation, and that's a whole other beast on its own. But for now, what we need to remember is that this is how you train a neural network to do anything. You clearly define its input, you clearly define its output, you tell it a measure of how far away its actual output is from what we expect the output to be. And once you define this difference, you compute this difference as a function of the weights. Then you take a gradient of the function with respect to those weights, and you make small nudges to the weights so that it gets better, so that the expected value gets closer to the true value. And eventually, once you keep doing this, you will come to the local minima of the cost function with respect to the weights, which is the best performance that you can get with respect to this network. Another way you can think about looking at these gradients is that it tells you which weight is most important. In our earlier example of the stereo with 2,300,000 knobs, there were a lot of knobs to tune, and we didn't know which one affected the output by how much. But if we calculated the gradient of the cost function, and we can see here, for example, W2 has an associated minus, so we can just directly correlate this. This is already a negative value. So it says that minus 1.25. So that means that this weight affects the cost function a lot more than, let's say, W1, which should only affect the cost function by 0.03. So you can probably increase this just a little because it won't make that much of a difference to the cost function, but this makes a lot of difference to the cost function. So this also gives you an idea. I mean, the true meaning of this, the geometric meaning of this, is the direction of the slope in 13,000 dimensions. But that's not as easy to understand, I would say. Anyway, this is, now that we have covered how the neural network could learn, I would like to mention here that there's a lot of degrees of freedom here. There's a lot of layers that you can put. There's a lot of different types of neurons, activation functions. In fact, it's this kind of flexibility that allows neural networks to be generalized to so many different kinds of problems. And it's also the reason why we cannot sum up all of neural networks in just a half an hour talk. But I feel like this intuitive idea as to how they learn and what you're actually doing every time you're training a neural network is really important to know. As we get into practical problems, there's one practical problem that I would like to address. When we were speaking of our cost function, I left out an important thing. When you calculate your cost function, you're actually supposed to calculate your cost function for a particular set of weights over every single training example. So for example, if you had 50,000 handwritten digits, you would have to calculate the cost over all 50,000 digits for one particular set of weights, divide the cost over all training examples, and then use the gradient of that cost to make an update. So to make a single change to one of your weights, you would have to go through the entire batch of training examples every time. And this is prohibitively expensive in computational time. So in fact, what we do instead is we do this thing called stochastic gradient descent, where we calculate our gradient over a mini batch that is a subset of the data set. And we use this gradient to take a step in some direction. You can see this diagram on the right here, which compares actual gradient descent, which makes its way directly to the minima, versus stochastic gradient descent, which sometimes takes steps in the wrong direction, but eventually also makes its way to the minima And it's much faster in terms of computational time because you're calculating this gradient over a small subset of the training examples. And clever tricks like this are used all the time in neural networks to improve its training and improve its accuracy and so on. But this is one of the most important ones, as you cannot calculate your cost function over the entire gradient. This is also a thing that I felt mentioning because batch size is a parameter that you usually have to pick in neural networks every time. All right, now that we have the general idea of neural networks in our head, like what they do, let's come to the specific problem that I wanted to show everyone how to code up today. So our problem is an image classification problem. So this is a image, these are images from the CIFAR-10 dataset. So they have 10 classes as a whole. The two classes not pictured here are planes and automobiles. As you can see, it's pretty hard to make out what class these belong to just for us humans too. And this is because the size of the images are 32 by 32. There are 32 by 32 pixels here, so it's not exactly the clearest image. However, that's really beneficial to the neural network because that means that it needs to store much less values in its memory, and it's thus better for us for the simple example and for ease of computation. So again, what do we want our neural network to do? We want it to take one of these images in, so which can either belong to one of 10 classes. And each of these images is also in color. So not just is it 32 by 32 pixels in the height and width dimension, there are also 3 channels corresponding to red, green, blue, especially. So the input to this neural network will actually be a 3-dimensional array of 32 by 32 by 3 pixels. However, at this point, I would like to talk about the different kinds of layers that we use. The previous problem, we used only dense layers, which are just simple neurons which activate between 0 and 1, and they're all connected to the next layer. However, that feels like it's losing some of the information, doesn't it? Because when we look at these, how we identify some of these classes is by looking at their 2-dimensional patterns. Like what I mean is, excuse me, if you have a ship, for example, you probably know that there's going to also be a picture of water in the same slide. So if you see a lot of blue at the bottom of the image, there's a high chance that that could be a ship. And that's one form of pattern. You also know that a ship is likely to be more angular than, let's say, a dog or a frog or a deer or something like that. So maybe sharp corners are something you can look for and then use that to classify it as maybe a plane or an automobile or a ship. The point being, we can probably make use of some of these 2D patterns. So it's not very conducive to our image classification problem to squish everything into one long vector, like we talked about for the image classification problem. So what is this thing that could help us identify 2-dimensional patterns? And that brings us to convolutions. Convolutions are a process which involves multiplying a section of the image with a filter. Now for this, I'd like to show everyone this wonderful live demo I found. So this is what convolution does. This is our input over here. So in this case, this corresponds to the image classification, digit classification problem again, but I'll tell you why it is useful to identify 2-dimensional patterns. What a convolution does is, for any value, like for this particular value, how you get the value of this output is, you see the two 3 by 3 grids that are highlighted. The one which is at the top of the screen corresponds to the filter. This filter is something like a neural network weight. It's something that we don't come up with, and it's something that the network learns by itself. But what the network does is convolves this filter with the input. And what that means is multiply each value of the input element wise with each value of the filter until you get this value. So for example, it's going to multiply 0 times -1 and then 1 times this value. But as you can see here, it is only applicable for elements which have a neighbor. So only these inner values count, and these outermost values will be eliminated by the output process. There's a way to ensure that this doesn't happen. But first, let's see how this looks. Let's let this go through the image and see what the convolution looks like and why it might be important. Okay, so so the filter that the convolution had chosen for this particular problem had all minus ones on the left, ones in the center, and then zeros on the right. So as it convolved itself with each element in this input matrix, we got this output. What does this look like? This kind of looks like it is identifying the left edge of this diagram, right? Like, because there's no activation along the horizontal line, but there's an activation and it seems to be detecting the left edge. This would be tremendously useful, right? Because if you had another filter that could detect bottom edges and then maybe right edges and top edges, you could identify all of the different components that make up the number, and this is exactly how we expected to solve the problem in the first place. So let's look at what this filter is called. This filter is actually called the left edge filter, and what it is doing is, and you can see how it works. So let's pick a point here where the value is really high. So this value is 2 right here, and the reason why the value is 2 is you can see that the input, there's a section of zeros right before. So those zeros, when multiplied with the negative ones, do not affect the output at all. But there are activations in the middle, which all correspond to the ones. And there are no activations on the right in the filter, which correspond to some finite numbers in the input as well. So whenever there is a transition from vertical zeros to vertical numbers again in the original input, this filter can pick it up. So what that means is that this filter is capable of detecting a left edge. So there are different filters for us to try. So for example, let's try a bottom edge filter. Wow. So at this point, you can see that correctly the bottom edges are identified by this filter. And you can use this, and there are many different kinds of these filters. And as you can imagine, if the neural network is allowed to pick any of these, it can come up with much weirder and much more interesting filters, which all affect the output in different ways and capture different features. So a convolutional layer in your neural network would do this. It would take it as input, the two-dimensional input of whatever image that is used, and present as output some kind of modification to it in which only the salient features remain. For example, the edges in this case. So edge detection is hugely useful, right? So going back to this, convolutions can now be used in our network to provide a more effective image classification algorithm. So I feel that this is how our neural network would end up looking when we actually try and classify these images. This image on the left here shows what a Gaussian filter does to the image. You can see that this image is very grainy. And if I ran the edge filter through this image, it would pick up all of these erroneous edges, which are not really edges in our eyes. But when you run it through the Gaussian filter, which kind of smooths out the image, you can see that the edge filter would pick out more distinct edges and more edges which are corresponding to the actual image. Okay, we are done with the boring part of the presentation, and now we can move to actually coding in Python. Uh, at this point, I'm going to switch to the Jupyter Notebook, and if you all have the Jupyter Notebook, it would be great if you wanted to live code with me. I would recommend that you run this notebook in Google Colab, because it has all of the packages installed previously, and it also has a GPU available. I'll wait for a couple of minutes here in case you want to pull this up. So this is how you would do it. You would just type Colab into your Google and then click on File and Upload Notebook, and then change your runtime to get the GPU. I can show you this on the actual browser. So File, Upload Notebook, and then runtime here. Make sure you change your runtime type to GPU and click Save here, because that will vastly improve your computational times. And then we can step through the notebook and talk about the code. I'll wait for a couple of minutes here because this might take some time. And in the meanwhile, if anyone had any questions, could just take a couple of questions now if you had any questions. All right. I don't think there are any questions. So let's just go right ahead into the code. So at the beginning, you will have to click connect here. So this shows how much. So this is all being done virtually. So you're using the Python 3 Google Compute Engine, and you are going to use this to train our network. I've intended this. I mean, if you didn't attend the workshop and if you just got the Jupyter notebook, you could still completely classify the data set and it would work completely fine. But this is uh, this is meant to stand alone and works on Google Colab. Okay, this section of the workshop is divided into these 5 bits. The main sections really are the loading and processing of the CIFAR-10 data set, and then defining the structure of the CNN, and then training and prediction using the convolutional neural network. So we are just going to do exactly the things that I previously told everyone about. We don't need to worry too much about this import section. We can talk about the packages as we use them. But all right, moving on to the hyperparameters. The hyperparameters are used to control the overall learning process. So there are like model hyperparameters and algorithmic hyperparameters, but because of our previous explanation here, it makes it very clear what we're attempting to do in this particular problem. So for example, the number of classes that are possible, that is the number of outputs, are 10. So we know this because there are 10 types of images, airplanes, automobiles, and so on. And batch size. Batch size is related to stochastic gradient descent and what we just talked about. And it's the number of inputs over which the cost function gradient is calculated. As you can imagine, the closer you get to the full size of the data set, as in if this batch size approaches the full size of the data set, it will take longer and longer, but you might get better and better results. So, and finally, the number of epochs, or this is the number of episodes the neural network is trained for. That is, you have the data set, and this is the number of times you want the neural network to go over the data set and learn. Here, if you have your own code with you, I would recommend changing the batch size and the number of epochs and seeing how this affects your final prediction and how it looks. But yeah, don't make this bigger than 30 or 40, because it takes around 30 to 40 seconds and it might exponentially blow up if you put a lot of epochs. Batch size 64 is also pretty decent. This network does reasonably well. We will see. Anyway, going into the loading and processing of the CIFAR-10 data set. There are a number of things that we have to do to the data set before we can directly start using it. These are called pre-processing and things that make the learning process easier. From here on, I would like to add this disclaimer. You will have a lot of questions like, why are we doing this specific thing in this neural network as opposed to doing something more general? And this is because there are so many degrees of freedom in a neural network that I just know what makes this one work. Like I know what makes the CIFAR-10 dataset classification algorithm work well. And hence I know what to do before actually doing it. But what I think this is really useful for, like this particular section of code, is this is how you can work through every single machine learning problem which you tackle through TensorFlow, because TensorFlow has the data sets with it, and really you have freedom to mess with it and define the structure of the CNN and train and predict as much as you want. So you can use this code to build your own neural network and see whether you do better than me or any of the other state-of-the-art people who have tried to classify the CIFAR-10 data set. So initially, we write a function to squish the image range value from 0 to 255 to 0 to 1. Now, the input of the image, the 32 by 32 pixels that are the height and width of the image, these pixels have a value from 0 to 255 because these are RGB images. But we would like the values to be between 0 and 1. This is because we know that the pixel values get multiplied by the weights of each successive layer as they pass through the network. And if they already start off as 0 to 255, we might have very, very big numbers somewhere in between. And this leads to slower learning. This is a tried and tested method that if you normalize your data to between 0 and 1, it causes the model to converge faster. So I would recommend doing this every time your data is not between 0 and 1. So in this case, what we're trying to do is just make the image go from 0 to 255 to a 0 to 1 float value. And what we're doing is we're taking the input as the image and the corresponding label, and we're returning the image and the corresponding label again, but this image will have a value between 0 and 1 now. Okay, we finally can load the CIFAR-10 dataset from TensorFlow datasets. So TFDS corresponds to TensorFlow datasets. There's a huge number of built-in datasets in the TensorFlow library for you to try your machine learning algorithms on. And this is one of them. This notebook is meant to stand alone. So I have described what each of the functions in between the TensorFlow dataset do. Like for example, in this case, we're importing the training data and testing data. Training data is the data on which the algorithm learns and is the data the algorithm sees. And test data is the data that the algorithm never sees but is expected to perform good on. And it's in fact the whole point of what we're trying to do. If the algorithm only performs well on the training examples, but not on examples it has never seen, then it is not a good model and it is not generalizable. Anyway, so this code may take 2 to 3 minutes the first time you run it if you are live coding along with me. And so when you go through it and you want to load the data set, you will need to specify the name of the data set. And with info equals true, I will show you what this info corresponds to. And you want to let the data set know whether you want the training bit or the testing bit. And finally, you give it a label saying as supervised is equal to true. What this means is that we want to treat this as a supervised learning problem and not an unsupervised learning problem. We're not interested in only learning the features. We actually want to do well on this specific task. So once you do this, this will take some time. Anyway, while that loads, I can show you the information about the builder of the data set. Look, so if you just type info, this is the same info that we're trying to calculate here. So if you type info, you get information about the builder of the data set, because as you can imagine, without this data set and its corresponding labels, none of these machine learning approaches would even be possible to try. So it says that the CIFAR-10 dataset consists of 60,000 32 by 32 color images in 10 classes with 6,000 images per class. There are 50,000 training images and 10,000 test images. So this dataset was compiled by the University of Toronto. And I am using this info thing to calculate the shape of the image, because we know this because we have already worked with this, but this is a more formal way of calculating the shape of the image by using the info image shape. You can also see other miscellaneous details which are already mentioned here. There are 60,000 examples, which are divided into 50,000 examples for training and 10,000 examples for testing. And you know that you will get an image with every data point and a label. All right, the data set seems to have been downloading. And finally, you can see some examples from this data set. So this is the same image that I showed you in the presentation, and you can see what each of those images kind of look like. The last step in the pre-processing of the data is to apply, repeat, shuffle, and batch to the data. So I'll explain what each of those three do. The repeat function causes the data set to repeat indefinitely. And let's just hold off on explaining this for a bit. Let me first explain shuffle to you. So because the data set comes in the same order every time, shuffle reorders the data set randomly. And what we do is we shuffle the data set randomly and then repeat it. That is, you shuffle the data set once, you add a copy of it to it again, and this copy of it is again shuffled. So essentially, these two functions used together create an endlessly repeating data set in which the order of the elements is not the same as the ones during the first time. Here, I would actually advise a word of caution, because if you use repeat, that means that your data set will repeat indefinitely. So you need to be careful when training your neural network, because it might cause it to go into an endless loop. So you need to clearly define when the end of a single episode is. Like, you need to tell it how long you want one episode to run for when you use this function, repeat, causing the data set to repeat indefinitely. And finally, you want the data set to be grouped in terms of these batches. These mini batches are related to what we talked about in the presentation. So batch determines the batch size of the neural network and is the number of inputs over which the gradient is calculated. It is the block which is fed to the network at one point, and the gradient step is calculated over that point. This block over here is essentially a combination of all three of these functions. We use this map function. This map function uses the inbuilt GPU. So once we run this, we have two data sets, DS train and DS test, in which the training data set repeats endlessly and is always shuffled each time. And we have a testing data set for which the same thing is true. So here you can see that batch size is controlled by this parameter, this variable batch size, which we define all the way over here. So 64 right now. All right, so our data set is now loaded and ready to be manipulated. So the next step that we have is to define the structure of our convolutional neural network. So going back to the presentation over here, yeah, you can expect that this is somewhat the shape of the neural network as we go through it. So we expect a few convolutional layers, and then pooling layers, and then flattening. I'll explain what these layers are as we go through them in the notebook. But here I've tried to be as detailed as possible in providing the documentation for each of the filters that we have used. So initially we'll create a function called create model. This is a user built function which takes the input shape as an argument and outputs a model. This model is a virtual object in Python memory. So what the model does is it relates these inputs to these outputs and has the connections stored between it. So it's essentially storing the structure of the neural network in computer memory. So functions such as training and inference can be run on this virtual object. So our next aim is to create a sequential model. Everything I talk about from here has documentations linked to it. So you can click on it and see what kind of definition these things has. So you can see that tf.kraster sequential groups a linear stack of layers into a model. So that's what we're trying to do in the first place here. So we first create a sequential model. So now that we have created a sequential model, we need to add layers to it. So these are the types of layers that we will be using in our particular problem in this case. So the layers we will use are the two-dimensional convolution layers, which we just talked about, a max pooling layer, and dense layers. So we should already know about convolutional layers and dense layers because we talked about those in the presentation. The max pooling layer, what this does is effectively it reduces the size of the layer. So going back to this image would be a helpful way to say it. You can pick a pool size. So let's say in our particular problem here, our pool size is 2,2. So that means that 1, 2, 3, and 4, this 2 by 2 grid of the input, you take the maximum value of the element amongst these 4 elements, and then you replace these 4 elements by that single element. So what you're essentially doing is you're cutting down 75% of the data in the input, but you are doing it meaningfully. Like you're trying to extract the maximum value from those 4 and then reducing the input by 75%. Now, there are guarantees as to why this will work, but for now, let's assume that it works and it retains all of the essential information from the image. If it does retain all of the essential information from the image while also reducing the image size by over 75%, what that's doing is creating a funnel essentially in your neural network. It's taking this big input size and it's making it compress into a much more manageable size. So max pooling is generally used to ensure that the computational memory required is reasonable, and it also prevents overfitting. So finally, we use your dense layer, just your regularly densely connected neural layer. Don't ask me, ask tensorflow.org. And finally, the other functions that we will use apart from these three layers are these activation, dropout, and flatten. Just a second before we move on, I'll talk about what these individual parameters convolution 2D takes. Filters. This parameter indicates the number of filters that you want to have. So for example, here you have in this list here, you have around 12 filters, right? And these are all user defined filters, but you want the algorithm to be able to identify these filters. So you can put as many as you wish, but normally people pick a power of 2, and I picked 32 filters. So that means that when in the first layer, so that means that once the image goes through this first layer, it'll go from size 32 by 32 by 3 to 32 by 32 by 32. So that means that it will be a 3-dimensional block, which is this big. Here you'll notice another parameter known as kernel size. So the kernel size corresponds to this 3 by 3 grid. So this is also 3 by 3. So this is what the filter would look like. And padding equals same. So this is an important one. You can see that when we go through this image right here, the size of the images reduces by 1 on the side, right? But you want the input and output to have the same size as it is propagating through the network. So what you do is you pad the output image with same. So if you say that you want the padding to be the same, that means that the output and input will have the same size, and it will be padded with the values that the algorithm feels is more appropriate. Most likely, it will be copying the values on the boundary again on the edge. So those are the three layers that we use there. And the other functions used by the model.add function are activation. This is pretty straightforward. It is the activation function that you use or that you perform on the output. There are many different kinds here, but I have told you about two in this. So the sigmoid and the relu function. And now the other function that we use here is the dropout. So dropout is a regularization technique which is used for reducing overfitting in artificial neural networks. The point of this is dropout isn't too relevant to the theory behind this workshop. You can look at it on your own, but it essentially forces some percentage of the weights going from one layer to the next layer to be 0. This parameter helps with overfitting, and it's really useful for generalizability. So we generally use dropout in image networks. And finally, flatten. So flatten is used for when we go from these cube layers to this vertical single vectors again. And what we hope is that through these cube layers, we would have identified some kind of features that can be then represented by single numbers here. And then once we flatten the layers, we go through some fully connected layers. So let's go into the actual creation of the neural network. So you go through, you first create a sequential model. You add a convolutional layer that has 32 filters. Then you add an activation layer, add a convolutional layer again, and another activation layer. So you keep going this way. So there's a max pooling layer, there's a dropout layer in between. And how do I know that this is the order in which these things go? Just based on previous experience. This is the hardest part to quantify to someone who's just learning machine learning, because these are just tried and tested methods that have worked before. And if we go in this way, we know that we can be assured of a reasonably accurate system. But as you can see here, there's a lot of parameters to change. Each one of these, like maybe if I remove this layer, maybe it performs better. Maybe if this activation was a sigmoid function, it would do better. There are lots of degrees of freedom, and which is the reason why they are so powerful in the first place. So the order would go like we go convolution layers, drop out, go through convolution layers again. And we keep going through the convolutional layers. There's actually 1, 2, 3, 4, 5, 6 convolutional layers in our neural network. And as you can see here, they keep increasing in size as well. So initially they're 32, then they're 64, and then they're 128. But you got to remember that this is the depth dimension, and the physical size is actually reducing each time you go through this max pooling. So that's the reason we have the liberty to pick bigger and bigger filter sizes as we go through the network, and now cannot do that initially. So until the max pooling layer kicks in, you cannot increase the number of filters like this. Anyway, once we pass through the convolutional layer, finally, we can get to flattening the convoluted layer. So we add a flatten, and then we add a couple of fully connected layers. So we add a model.dense, and then we add a model.dense. And you will notice that the output of this layer is num classes. So this will be 10 because we want our function to have 10 outputs. And finally, this uses a different activation function, one that we haven't covered before, but you can check all of those activation functions here. Now we can print the summary of the model architecture and then pick three very important things. So when we initially talked about the definition of machine learning, we needed experience, we needed a performance measure, and we needed a class of tasks, right? So the class of tasks in this case is image classification. The performance measure is what we denote to be our loss. So in this case, we are choosing our loss to be sparse categorical cross entropy. You don't need to know what this means. You basically need to know that it's a specific performance measure that you need to optimize over, and which when you optimize over it through experience, you get better at this class of tasks. The other thing you need to specify is optimizer. Optimizer is the optimization algorithm you use for improving performance. So the algorithm that we talked about in the presentation was stochastic gradient descent. So you would write SGD here instead of that. But I am using the Adam optimizer for this one because I know that it works better. Finally, the metrics to be evaluated by the model during training. So this is the interpretable metrics, because this loss, the sparse categorical cross entropy, isn't really an interpretable metric for us right now because we don't know too much about it. But accuracy is much more easy to understand. Accuracy is just defined as the number of correct classifications versus the number of total classifications performed by the network. So let's go ahead and run this block. Since it's a function, it won't have any output. But then when I actually call the function, this is what it looks like. You can see the sequential model. It will tell you each layer in the network. It'll say conv2d, conv2d1, then conv2d3, 4, and 5. So we know that there are 6 convolutional layers because the index starts at 0. And you can see the number of weights that are there in each continuous network. So you can see that activation layer doesn't really have weights, but convolution again adds weights and so on. And you can see the number of weights blowing up with each successive convolutional layer until finally you have 2,395,434 parameters. It's a lot of parameters, and it's not simple to tune this by hand. So you can see that there are trainable parameters and non-trainable. So you can force some of them to not update during the process in case you know something about the physics or something like that that no one previously knows. And then you also have the trainable parameters. So these are the ones that can change during the learning process and hopefully will help us learn a little bit more and hopefully correctly classify the neural network. Okay, now the time has come to train the model. So right now what we have done is we have done model.summary and model.compile. This configures the model for training and other things. And once you create the model, you create a directory for results. And then you train the convolutional neural network. So this is just in case the results are already stored, in case you are running this model again and again, it'll just load the weights from the previous data set. But in case you're fitting the model for the first time, this is how you need to do it. You need to say model.fit, and you need to define the training data set. Apologies for the noise outside if it's a little too much. You need to provide a training data set to it. You also need to pick the number of episodes. So this was picked at the start. So it's telling you that this is 20. Google Colab is telling you that it's 20. Validation data that you use is going to be the test data set. Verbose equals 1 tells you that it's giving that you want it to output all of these metrics, that you want it to tell you how it's going through the training process. And here are two very important steps that ensure that you don't descend into endless loops, because both your training and test data sets are infinite. You need to say that the steps per epoch, that is the number of times you go through the data set, has to be specified by this. And it says that it's the number of examples in the training data set, which we know to be 50,000, divided by batch size, which is 64. So what that means is that you only take 50,000 divided by 64 steps through the data set before you reinitialize and start a new notch. This indicates to the training algorithm when to stop in the data set. And similarly, you need to mention that while validating as well, you need to provide the stopping condition for it. You need to say validation steps. Now, if you didn't have these two lines, you would end up in an infinite loop. But if you remove these two lines, then I would suggest that you also remove this line, that repeat, because if you repeat and then don't add an end for the training episodes, you're going to end up with an infinite loop, and that's not great. It's possible to break this model even on a virtual system. But anyway, let's go ahead and train the model. So it's the first episode. It's the first time it's passing through the cell. You can see how long it's taking down here. So 781 is 50,000 divided by 64. Is that right? Yep. And round it down to the smallest value. So 781 of 781 means there are 781 batches in the data set, and that's how many you want to go through before reporting to me the loss. So in this case, this loss is sparse categorical cross entropy, which isn't really the most interpretable metric. So we can look at accuracy instead. So it says that already with just one pass of the data set, we can classify 40% of all images that we saw in the training data set accurately. But this is surprising. It can classify even more of the training testing data set accurately. So validation accuracy, it can classify 56% of all elements in the testing data set accurately with just one pass through the network. So you can see how much time it takes to go through all of this. It tells you how much time it takes per step. And you can see what is our most important thing, that the loss reduces through experience. So you can see that 1.61, 1.12, 0.92. And if this isn't reducing with every episode, you know that you've done something wrong. You know that it isn't a clearly defined machine learning task, because your performance measure is not improving when you have more experience. So you can see it chugging through the system, taking steps. We're getting to some pretty good values over here. So ignore this loss, but it's able to classify 80% of all images successfully, and 80% of testing images too. So while this runs, I want to show everyone the CIFAR-10 Wikipedia page. And the reason I'm showing you this is there's a section for research papers claiming state-of-the-art results on CIFAR-10. So this is a table which lists the error rate on the CIFAR-10 data set across all different possible algorithms. So if you filter by error rate, look, there is this efficient training of giant neural networks using pipeline parallelism that achieves 99% accuracy on the testing data set. Of course, with so many degrees of freedom, it's impossible to say what all they've changed in the actual neural network. Maybe they're not even using convolutions at all. But if you wanted to play around with this code and come up with your own algorithm, this is who you're going up against. So we can wait for this network to finish training. Okay, we're getting better on the accuracy. It seems to be getting to 87% right now. Oh, actually going lower. So at this point, the network is close to whatever best value it could possibly reach, because it seems like the validation accuracy has tapered at around 80%. All right. So our neural network has completed training, and it's the final values that it reports are an 88% accuracy on the training images and an 80% accuracy on the testing images. So just to remind everyone, the classes are airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So let's see how this network does for an individual element. All right, so this is the image, pretty clearly a bird. So the output of the neural network is 0.01 and 0.99. This network is very confident that this is in fact a frog, whereas this is a bird. So this is one of the cases, and this is one of the 20% of cases in which it'll be wrong. But this is very funny to see because we can see why the network thinks this is a frog. There's a green background in the back. It's brightly colored like some frogs are. And there is some activation in 0.01. So it does think it is very mildly thinks it's a bird, but it's wholly wrong. And it's confidently classifying it as a frog. So let's see whether it does better. Okay, this one's clearly a bird and it seems to have no problem identifying it as a bird. There's a strong one as a output as the one of the networks, and it thinks that this is image is a two. So very clearly thinks that it is a bird. So the actual class that this image belongs to is also two. Okay, zero classifies airplane. So our neural network thinks there's a 0.97 chance it's an airplane, but also a 1% chance that it's an automobile and a 1% chance that it's a ship. I told you, right? It'll be trying to identify things like angular shapes in the thing. So once it notices that there are angular shapes, it could only possibly be an airplane, automobile, a ship, or a truck. And you can see that there are activations in three of them. When the images are much more clearly defined, you can see that the network has no problem. It reports a strong one, and there's no deviation between what the class of the image the neural network thinks and the actual class it is. Again, an airplane, not a problem. I'm looking for some more interesting things than this. Oh, okay, this is a fun one. So it thinks there's a 93% chance that this is a dog, but there's also a 7% chance that it could be a cat. So you can see why it would think that. We know that this is a dog because in our unblurred head, when we unblur this image in our head, we can clearly see the dog shape, but it can see eyes, a nose, and all of these prominent features. So you can see why it can be confused and into thinking all of this. All right, I think that's a reasonably good network, and that's a good place to end it on. I have included this link here. So in case you wanted to try better approaches or try different neural networks here, you could maybe go through some of these neural network architecture search or something like that and try and improve your system. But anyway, I will stop sharing for now. Yeah, actually, I had one last thing to go through with actually. So some important things to mention here are a few caveats of this neural networks. So one main caveat that we saw, which was evident, was that there are too many degrees of freedom. What kind of layer you can use, what kind of parameters you can provide to the layer itself, how these layers are connected to each other, whether they're sequential or non-sequential, or whether they feed back to each other. And all of these degrees of freedom are good because they provide us, it's a hard problem. It's image classification is a hard problem. So you would need all of these different knobs to turn to try and fix it. But these many degrees of freedom also make it prohibitive for someone just experimenting to stumble upon something right. You would have to come up with a very systematic way of finding a neural network that performs really well. That's one big problem of neural networks. Another problem is generalizability. You notice that it did better on the training data set than on the testing data set. And this is true for all neural networks. There are some tricks about the training data set that it will learn based on repeated interactions with the training data set, which are not generalizable, which are only applicable to things within the data set. However, if the testing data set has some kind of input that is an interpolation of things that the network has already seen before, it will do amazing. The network has no problem dealing with these things if they're an interpolation. Professor Brunton has a good analogy here for when you might want to overfit professional athletes. So for example, someone who is a professional arm wrestler might be overfit to the sport of arm wrestling, but they might not be generally be able to beat a bodybuilder or someone in weightlifting. But sometimes you don't want that. Sometimes you don't want to be able to be generalizable. And the past examples that you see from during the training phase of the neural network is exactly what you want in the future phase. Like that it's going to be predicting similar things. So in those kinds of cases, generalizability isn't as much of an importance, and it's actually preferable to overtrain the network. However, when you're trying to find physical things, like for example, if you're trying to find the force law, for example, like F equals ma, just from feeding the network vision data and repeated data of a cannonball being flung or something like that, then that might be hard. It can exactly predict how a cannonball might fly, but it cannot apply that general principle of F equals ma to everything else. And finally, the black box system of adjusting weights automatically and inside with so many parameters isn't the best for interpretability. We don't really know what all of these mean. And while we can come up with like a physical significance for the filters that the convolutional layers eventually find, when we have dense layers and these densely interconnected number relationships between all of them, the mathematical waterfall, as I described, it's not really too easy to understand what's going on here. And it isn't the best to communicate to someone else. So right now, work is being done to ensure that neural networks are more interpretable, and some in-between layers can be used to provide some more useful, communicable information, if you know what I mean. But okay, stopping sharing now. So in conclusion, I hope this was useful to everyone who was here. And I guess the point of this was to provide a small primer and show everyone the concepts and then show you how the actual code works. I hope everyone liked it, and I'll stop recording now.